Humans have dreamed of leaving Earth, but the technology to build a moon base exists today for the cost of the ISS. Until now, our footprint on the lunar surface has been strictly temporary. We flew brief, daring missions to plant flags, collect rocks, and quickly leave. You can see that impermanence in the Apollo lunar module. It was a fragile, gold-foil lifeboat designed to keep astronauts alive for just a few days in a vacuum before they had to flee back home. That strict time limit was dictated by Earth's massive gravity well. Under the old rules of spaceflight, every single drop of drinking water, ounce of rocket fuel, and pound of shelter had to be hauled up from our planet's surface at staggering expense. You cannot pack enough supplies to survive indefinitely in a hostile environment. To actually stay on the moon, engineers have to solve 3 lethal bottlenecks: astronomical launch costs, constant cosmic radiation, and a freezing lunar night that lasts for 14 days. We cannot brute force a permanent settlement by constantly importing Earth's resources. We have to completely reinvent how we move cargo and how we build. The first barrier is getting heavy equipment off the Earth. Relying on massive, government-built rockets like the Space Launch System means spending billions of dollars on a vehicle that flies once and then drops into the ocean. A strategy called Moon Direct bypasses those legacy development delays by shifting to a different architecture entirely: commercially available, reusable rockets. Hardware like the SpaceX Falcon Heavy is already flying. Because the boosters fly back to the launch pad, the cost of lifting heavy payloads drops exponentially, allowing for frequent trips. This lower cost enables a new logistical strategy. Instead of launching astronauts and their habitats on one giant risky flight, we can separate the cargo from the crew. We can fly multiple, cheap cargo landers to pre-deploy the base infrastructure before a single human ever leaves Earth. Reusability turns lunar access from an impossible expense into a manageable freight pipeline. Once the cargo lands, it faces a surface constantly bombarded by solar flares, galactic cosmic rays, and flying debris from engine blasts. Shipping heavy steel radiation shields from Earth would bankrupt the mission. The engineering solution is In-Situ Resource Utilization, or ISRU, manufacturing with local materials. Autonomous robots equipped with high-powered lasers will gather native lunar dust, known as regolith, and melt it down into hard, ceramic-like blocks. This diagram outlines how the blocks become a modular shield. Interlocking cubic compartments form thick walls around crew habitats. An automated gantry stacks and fills the units with raw regolith, locking them together using specialized microfastener pads and strut tracks, entirely without human intervention. This is not theoretical. Terrestrial engineers are already using automated material deposition to 3D print large-scale structures on Earth, like this concrete building. Adapting this robotic construction to use raw lunar dirt cuts our supply line to Earth. The base builds its own armor. Even with a secure habitat, the crew has to survive the lunar night. At the poles, darkness lasts for hundreds of hours, rendering solar panels useless and draining chemical batteries. To maintain life support and industrial operations, we need continuous, robust energy. Generating 100 kilowatts requires a dozen football fields of solar arrays. A space-rated nuclear reactor delivers that same output from a wastebasket-sized cylinder. That continuous energy powers the heavy drills, pumps, and cryogenic plants necessary to mine ancient ice buried inside the permanently shadowed craters of the lunar South Pole. Using that continuous electricity, chemical plants can split the extracted water into hydrogen and oxygen, cooling them into liquid rocket propellant directly on the moon. Manufacturing fuel locally changes the entire math of lunar exploration. A lightweight lunar excursion vehicle could refuel at the base, hop to any location on the globe, and return, completely eliminating the need to haul return trip propellant from Earth. Solar power lets us visit. Nuclear power, and the local fuel it creates, lets us stay. These 3 technologies work in tandem. Commercial rockets/launch fees, robotic printing eliminates the need to ship heavy building materials, and local fuel production severs the umbilical cord to Earth. By replacing bespoke government rockets with a commercial logistics pipeline and building with materials found on site, the financial barrier to entry collapses. Current estimates from NASA and the private sector suggest we can build a fully operational moon base for $20 to $40 billion. We already know how to fund and manage a project of that exact scale. That is roughly what it costs to build and operate the International Space Station, a financial commitment humanity has sustained for decades. Establishing a self-sustaining foothold at the lunar South Pole is also a mandatory stepping stone. The systems we perfect to extract ice and print habitats will serve as the exact refueling stations and proving grounds required to send human crews to Mars. We are not born too early to explore the stars. We are the generation laying the first permanent bricks off-world. The economic blueprint is calculated, and the hardware is sitting on the launch pad. We only need the institutional will to execute the planner.